Good evening. Welcome back. Where have you all been? It's been a whole semester, so I mean, thanks for sticking around. It's great. Welcome to the 2013. I was going to say 2012, 2013. Let's just say the 2013 Planet Ocean Lecture Series, and I wanted to talk to you a little bit about the presentations. We're going to do 3 this spring, which is unusual, but we had a real opportunity. And before I introduce our speaker, let me talk first about the lecture that will be on March the 13th of this year, 2013. And this will be in UNCW's Lumina Theater. We're co-sponsoring with the College of Arts and Sciences and a variety of other groups to welcome Dr. Peter Sale, Professor Emeritus from University of Windsor in Windsor, Ontario, Canada. His very famous book, Our Dying Planet, is the subject of his talk. The title will be Global Change, Tipping Points, and the Urgent Need to Act, Solving Our Global Environmental Crisis. So join us there at 7 p.m. And they don't call them a buffet like we do. It's a reception at 8 p.m. But we did manage to get wine and beer at the... yeah, you're welcome. Yeah, you're welcome. We're trying not so happy you come for that, right? At any rate, that'll be really interesting. He is world-renowned and very hard to get to come to any university in the country. On April the 23rd, so many of you have been asking about the Marbionic building and when that will be ready for viewing. We will be doing a lecture and a tour of the building on April the 23rd. And that will be at a regular time of 6:30 p.m. Refreshments, I guess we call them refreshments now. Refreshments at 7:30 p.m. I'll do a little talking. We'll have Jeff Wright here to do a little bit of talking about the programs that are there. We'll introduce the whole Marbionic team that were responsible for getting the building, for administering it, and we'll talk a little bit about the Crest Research Park. I don't know how many of you saw that on your drive-in. The sign no longer says UNCW Center for Marine Science, it says UNCW Crest Research Park. And that actually stands for the Campus for Research, Entrepreneurship, Service, and Teaching. Okay. The university has expanded on the Centennial Campus idea from NC State to create a Millennial Campus at UNCW. So those are the events that are happening in the future. And now on to tonight's event. It's my pleasure to introduce tonight Dr. Dylan McNamara. He is an assistant professor in the Department of Physics and Physical Oceanography at UNCW. At the end of the night, we'll talk about some of the other things that he does for the university in terms of his extramural athletic activities. Dylan received his Bachelor of Science in Physics from Salisbury University, his MS in Physics from San Diego State, and his PhD in Oceanography from Scripps Institute of Oceanography in UCSD. Did some postdoc work at Duke University, and then became a professor here in 2008. He has very broad interests, and he'll talk a lot about that tonight, looking at things like floods, the effects of floods on human populations, why we shouldn't be building where we are building, and so forth. The title of his talk tonight is Flood, Fortify, or Flee, Linking Economic and Natural Coastline Dynamics. Dylan McNamara.
Thanks, Dan. Is this working? This microphone, can you guys hear me? I feel a little bit like a motivational speaker with this microphone. Is this thing even on? Is it on? Hello? Is that? Yeah, there we go.
Give me that.
Okay. Well, first I want to start out by just thanking those of you who have contributed to the Bluefish Society. It's kind of a strange time in science. For some reason, science has become part of the political discourse. And I don't just mean scientific results are into the political forum and then politicians have the opportunity to say what we should do with those results. But scientific results themselves have become a part of the political discourse. Politicians have, become accustomed to saying whether or not science is legitimate. And so one of the things that I think is critical at this stage is that scientists interact with the public. And I don't just mean through, I publish in technical journals, and those technical journals they're very important for my career, but to be honest, even some of my colleagues don't read those papers, let alone the public. So it's very important as scientists that we take the initiative to interact with the public and convey our results in a way that the public can understand. And so those of you who've contributed to the Bluefish Society, I appreciate the opportunity to do this, particularly as an early career scientist. I appreciate the opportunity to come here and speak to you about some of the work that I've done. So as Dr. Baden mentioned, my actual background, I went to my undergraduate degrees in physics, and I went to graduate school in just traditional physics. And I was doing research in laser optics, so I was shooting lasers around in the dark. And the room that I would sit in had to be so dark that I would have to take a tiny little flashlight just to write my results down on a notebook. And I grew up at the beach, and I loved being outside, and I had a reckoning one day, and I realized I don't want to do this. I don't want to sit around in the dark all day and shoot lasers around and do math and science with things that I'm not familiar with. I wanted to interact and deal with questions that struck me personally. And so I've had this question sitting up here, as you guys have been sitting in the audience, in some provocative pictures. This is a question that I'm interested in. What will the human-occupied coastline look like in the future? And so, first of all, what do I mean when I say, what will the human-occupied coastline look like in the future? Now, I realize, living at the coast myself, my relatives live at the coast, my friends live at the coast. Particularly since Sandy, there's a sense of jumpiness to coastal residents. Kind of looking over your shoulder and wondering what's going to happen next. And I think it's very important as a scientist to take the tools that I've developed in math and physics and apply them to a question like this. And when I say, what is it going to look like? I'm talking about the things that we care about. Not just the position of the coastline in the future, but where do people live along the coastline? What does the infrastructure look like? What do homes look like? Those are the questions that I'm interested in. So as you're looking at these pictures and thinking about what are the ingredients that would go into trying to answer a question like that, there's quite a number of them. Certainly physics, geophysical processes like erosion. What's happening to the beach in front of my house? I don't know how much you remember from your high school physics class, but one of the things you may remember is Newton's second law, F equals ma. Newton is playing a direct role in controlling where sand grains go. Newton is also playing a direct role in dictating how often storms occur and how storms themselves come about. Physics is important for understanding how the level of the sea rises. So physics is clearly important, but economics is also important, right? As we're existing along the coastline, there are these very sophisticated real estate markets where people are buying and selling coastal properties. They have investment strategies. So Newton's important, but also Adam Smith is very important. Understanding supply and demand and why people invest in the things that they invest in is very important for trying to understand how the coastline might evolve in the future. But then what is also important, this isn't an individual disciplinary endeavor. You can't just understand physics. You can't just understand economics to answer this question. You have to understand the interactions between the two. And that is something I want to talk about in a little bit more depth. So for example, here's a picture from Hurricane Irene last year. And this is an image that those of us who live at the coastline, we're familiar with. This is an example of where the physical coastal environment has certainly impacted the coastal economy. In this case, very obviously, it damaged that home. If I was to categorize this, though, I would say that this is an example of the physical coastal environment impacting the coastal economy from a short time scale episodic event. It happens over the course of a few days and it has dramatic influence on the coastal economy. So that's one type of influence of the physics into the coastal economy. You also have instances like this. Here's a quote from our local newspaper from, I think, 2007. Tax officials slashed the value of an undeveloped lot owned by this person 93%, from $1.3 million to $81,500. So this person lived on the north end of Figure 8, where they're suffering from, at the time, we're suffering from chronic erosion problems. So here, the physical environment that's impacting the coastal economy is not an episodic event, but it's a slow time-scale process. In this case, erosion playing out every day over years and years and years. And this slow time-scale coastal dynamic is impacting the economy. So that's slightly different than the storm. Here's yet another interaction between the physical environment and the coastal economy. In a new plan to deal with beach erosion and prepare for sea level rise, the U.S. Fish and Wildlife Service proposed changes that the mayor and others say would eventually drive away summer tourism and drive down the economy. So now, focus on this prepare for sea level rise part of that quotation. Now it's actually the anticipation of the changes that are going to occur in the physical environment and how they may impact the coastal economy. So expectations about the future impacting the coastal economy. They haven't even played out yet. So it's hard to talk about expectations of the future without mentioning our friends at NC20. You know, I don't know how much of this you guys followed this past fall, but you know, NC20 tried to pass a bill that regulated what we could say about what was going to happen to sea level rise in the future. And I'm not necessarily interested in getting into the argument of what is going to happen with sea level rise and whether these people were right or wrong. But what I find interesting about this is that this group was trying to control people's expectations about how the future environment would change because they knew that that has a dramatic impact on the coastal economy. And so if you think about the motivation for them trying to pass such a bill, it gives you an idea how important it is that expectations play a significant role in altering coastal economies. Okay, well, we certainly don't sit idly by and just allow the physical environment to impact coastal economies. Our economic engine churns and then impacts the physical environment. Here's a quotation in that regard. Already we've prevented $443 million in damages. Nourishment has already paid for itself and all planned renourishment cycles over the next 4 to 3 years. This is a person from the Army Corps of Engineers speaking about a beach town in coastal Virginia. So here, nourishment, probably all of you are familiar with nourishment. What nourishment is, you go offshore, grab some sediment that's beach compatible, and you pump it onto the beach to provide extra beach width and protection from storms. So we sit there and the coastal economy actually impacts the physical coastal environment, the reverse of what we were talking about a moment ago. But it's not this simple, and not everybody feels this way necessarily. Here's another quote. Beach renourishment creates a false sense of security that tends to induce development in the very areas where it's most likely to be destroyed by nature's worst. So here, someone's giving a counter to this idea that nourishment is so wonderful. But what's more important to me when I read this quotation is it's giving you some insight into these interactions are not just one way. So for example, the coastal economy can drive nourishment, but then this person is suggesting when that beach nourishment occurs, it then comes back and impacts the economy. So all of these things are critically linked together. So if we go back to that picture that we had early on, what are the things that we need to understand how the human-occupied coastline might evolve in the future? We need physics, we need economics, but we also need the interactions between them. We need to incorporate the way that economics impacts the physical coastal environments, beach nourishment, and mitigation, and then damage, of course, and people's expectations of how the future may change. And not only that, how those things all wrap together and feed back on themselves. Okay, so as a scientist, you know, how might we, and so we all kind of agree probably that we need to have all these things if we're going to try to understand over a sort of year to decadal time scale what's going to happen to the human-occupied coastline. As scientists, what mechanisms do we have to take a look into these dynamics? Well, one thing we could do would be to have controlled experiments. One of the East Coast's greatest scale model builders is in the audience tonight, but I wouldn't have to ask him to understand that that's a ridiculous idea. If I was going to sit here and say, I'm going to construct the entirety, a scale model of Wrightsville Beach and Carolina Beach, and maybe all the towns all the way up to the Outer Banks, and I'm set them on sand, put them in a wave tank, have waves come and crash against the houses, and then raise the level of the sea as well. I mean, that's totally absurd. And in addition to that, you'd have to have little automaton robots that you create that would run around and buy and sell these scaled little properties. So Dr. Bates didn't give me big enough lab space here at CMS to do something like this. So we can't, as scientists, we can't construct controlled experiments to understand all those dynamics that we just talked about. The other avenue that scientists have, of course, is to go out and collect some actual data from the system. Now, this seems like a reasonably good idea, but the problem in doing this with this particular question is that there's not enough data. If you want to do data analysis, you have to have a really large data set. As an oceanographer, if you want to study waves in the surf zone, you can construct your instruments, you go plop them in the surf zone, let waves crash all over your instruments for maybe a few weeks, and you will just have a plethora of data to go and analyze. If instead you're interested in how humans interact with the environment at the coastline on a community scale, what they do to the coastline, then how the physical environment changes, how that then changes the coastal economy, and you don't just want to do it for one town. Of course, when you nourish the beach, that affects towns up and down the beach, so you have to do it for multiple towns. There's just not enough data out there. Wrightsville Beach has been nourishing for decades, it's true, but if you want to do the whole coast of North Carolina, there's not enough data to go out there and rigorously probe the system to get some insight into how the dynamics work. So what does that leave us with? Luckily, it leaves us with my specialty, is constructing models, okay? And I realize that when you say that term, I use it all the time. It's not obvious to everyone what that means. When I say construct a model, scientifically, when you construct a model, there's a number of ways you can go about doing that. One is you can construct in your mind a conceptual model. And scientists do this all the time, and it can be very useful. But what I'm talking about in this particular case is a quantitative model, a rigorous quantitative model. That is the only way, if you really want to get insight into understanding the dynamics of the human-occupied coastline, and you want to make some predictions about what's going to happen in the future, and use those predictions to inform policy, you have to have a rigorous quantitative model. You can't just have a conceptual model of how the system works. So if we go back to those quotations and the pictures that I was showing and kind of put it into a formalized structure, the way that I would construct such a model is you take the coastal dynamics, the things that, beach erosion and so forth, and coastal economic dynamics, and they become linked together through the damage that occurs to the coastal economy, as we talked about, through people's observations of what's actually happening at a given moment in time, but also people's predictions and expectations of what's going to happen in the future. And then the coastal economy impacts the coastal dynamical system through beach nourishment, for example. And you construct a model that wraps all these things together. So you build a numerical model. You come up with rigorous equations that control each of these processes, and you put all of that inside a numerical model. And then you investigate things like, what's going to happen with sea level rise? What if sea level rise is this? What if sea level rise is this? What if we have this storm behavior for the next 50 years? What if we have this storm behavior for the next 50 years? And you can probe the system on the computer to find out how it's going to evolve. And as I mentioned, it has to be quantitative and rigorous, because here's a little thought. What if the scientific community just decided that all the data was suggesting that sea level was going to jump 1 meter in the next decade? What do you think would happen to the human-occupied coastline, say Wrightsville Beach, for example? There's a host of possibilities. One is, will it flood? Will people just sit there and then the storms will come and their houses will get crushed and they'll just get flooded? So will it flood? One possibility is maybe they'll fortify. Maybe they'll increase beach nourishment, they'll raise the dunes higher, construct seawalls maybe. So maybe they'll flood, maybe they'll fortify, or maybe they will just have a fire sale in their coastal properties and everyone will say, oh man, we're out of here, we're leaving, sea level's rising a meter in the next decade, I'm out of here, and they'll just sell their houses. So will they flood, will they fortify, maybe they'll flee. So after that 15-minute introduction, the title slide to my talk. I hate giving title slides as the first one. That's just so boring. So flood, fortify, or flee, and linking economic and natural coastline dynamics. As I mentioned, this idea that we need to bring the things together if we want to answer these kinds of questions what's going to happen to our coastline. And I have to mention some of my colleagues. This work certainly stands on the shoulders of some of my colleagues. And I have developed a little team of people working on this problem. We're all sort of North Carolina-centric. Andy Keeler, who's at the Coastal Studies Institute in Manio, and Marty Smith at Duke, and Satya Gopalakrishnan, who was at Duke as a PhD student, who's now a professor at Ohio State. All fantastic resource economists. And then my good friend, Brad Murray, who's a coastal geomorphologist. So we put our brains together and try to tackle these kinds of problems. And a lot of the results I'm going to show you today are results that have been influenced by my work with them. And the National Science Foundation has been generous thus far. I hope they'll be even more generous in the future funding this work. Okay. So a brief outline for what's to come. I'm going to tackle this question: what does the future hold for these human-occupied coastlines? And in order to do that, I want to go in depth a little bit more with you and describe how the system components work, and then describe how they're actually reproduced in the model. And my promise to you is that there's no equations in this talk. One of the things that we should be able to do as scientists, no matter how mathematically rigorous our work gets, we should be able to convey that to the public. You shouldn't have had to have multiple semesters of differential equations to understand a topic like this. So there's no equations. I'm going to try to sketch how these models work without digging into the math whatsoever. And then when you put all that stuff together, I'll show you what the results are from these numerical modeling experiments. And then very briefly at the end, I'm going to talk about right now, because these are questions that we're going to tackle about the future. I'll talk about right now using the same model. If you just change one little piece of it, it's telling us some interesting things, I think, about the state of our human-occupied coastlines today. Okay. So in going back to this is kind of going to be our roadmap for describing what's in these numerical models. I'm going to pick this apart piece by piece and just talk very casually about what are sort of the interactions that make up a model like this. So with respect to coastal dynamics, being coastal residents, all of us, we're sort of familiar with a lot of these things. So we're talking about, erosion. When storm surge occurs and waves are on top of the storm surge, it comes up, it chews the beach, it grabs that sediment and moves it offshore. Accretion also occurs. When the waves are small, accretion can push sediment back up onto the shoreline. So that's what I mean when I say coastal dynamics. In addition to that, the models that I'm going to be talking about are focused on barrier island coastlines, like we have at Wrightsville Beach. And one of the important processes on barrier island coastlines is overwash. And what that is just what's indicated by those red arrows. When you have storm surge, when the onshore winds blow up a pile of water at the coast, and you have waves on top of that, it chews sediment from the front of the barrier island and then places that sediment on the top and on the back side of the barrier island. And that's termed overwash, and you can see the indication of it right there. The recent storm just hit that coastline and deposited all that sediment on the back side of the barrier island. There's also a longshore sediment transport, right? These processes are primarily in the offshore and onshore direction. There's also processes that go in the up and down the coast direction. And that's what a longshore sediment transport is. The gist of that is that when you have waves that come towards the coastline at an angle, they, to use the fancy physics term, they deposit momentum flux in the surf zone, but the point is that they drive a current. If you've ever been to the beach and put your towel down and hopped into the water, and then come out of the water and you floated down from where your towel is, that's the longshore current advecting you down the beach. Of course, when waves crash and they stir sediment up, that sediment gets brought up into that river and then gets taken down the beach. And you can often see the indication of that when you have beaches like this with jetties. You can see that there's accretion on one side and erosion on the other, and that's a manifestation of this sediment that's getting carried or advected in the longshore current. And of course, inlets, very dynamic entity that exists along barrier island coastlines. You have this hydrodynamic forcing of the tide comes up, water rushes into the inlet, it eats up some sediment, it throws that sediment back into the back of the inlet, tide recedes and it eats up more sediment and throws some out into the mouth of the inlet, and you get ebb tidal deltas and flood tidal deltas. So if I'm going to construct a numerical model, the module that has to have coastal dynamics has to reproduce all of these processes and more. So how's that done? Well, you have to take some liberties. You can't imagine coming up with your Newton's second law equation for every single sand grain that exists on a coastline, that's completely impractical. So you have to come up with some abstractions. You have to kind of represent your system, in this case a barrier island, a little bit more simply than it actually exists in nature. And so in the case of the model that I've constructed, and this is a model that I constructed while I was a PhD student, I represent a barrier island in this very simple shape that you see here. Okay, so this is the ocean over here, the lagoon side here, the top of the barrier island right here. So by representing it this simply, all I have to do is track the three-dimensional location of these what you call nodes in space. And so if those nodes move around, that means that sediment is either being eroded or accreted along the barrier island. So for example, when a storm comes in the model, this node right here moves backwards. And so you slice off a little piece of the barrier island, and you take that sediment and you send it somewhere, according to some equation. You may send it up and down the beach, this way, with the alongshore current. You may send it on top if it's overwashed. And then you can exchange it with other places. The sandbar reservoir, which is just meant to represent, a pile of sand that's sitting offshore. You could exchange it with the ebb tidal delta reservoir. You have a bunch of different options, and you just have some mathematical equations that tell the model what to do with that sand. In addition to that, sand can be exchanged with the dune. You have a very simplified representation of a dune in the model, and you can exchange sediment with the dune as well, and vegetation backing the dune. So the model then is forced with a number of things. One, storm surge. That is what drives a lot of the sediment changes that happen along the barrier island. So what I do is I literally go back and look at the last 50 years of storm surge data, come up with the probability of a storm surge of this size, the probability of a storm surge of this size, and so on and so forth. And I take that storm surge information and I use it to impact the barrier island. I have waves in the model. Of course, waves are very important. I have rising sea level. I have wind. Wind's a very important process that grows the dunes. And when you force the model with all of these things, you simulate each of these processes and more. The processes that I talked about a minute ago when I was describing how the coastline works. Alongshore sediment transport, erosion, accretion, overwash, etc. So suffice it to say, without getting into the details at all, that this process and this model is well vetted in the literature, which is to say that the way that this model works reproduces. I go out and grab actual data for how a barrier island evolves to the best of my ability. I compare how the model does to what actually happened in nature, and the model does a pretty good job of reproducing the way that barrier islands actually evolve. Okay? So that module then is unto itself. That's the coastal dynamics module. The next thing we have to tackle is the coastal economy. How does the coastal economy work? Well, that's something that we're much more familiar with. We're probably all actors in the coastal economy. And you can get, along these coastal stretches, pretty significant high-density coastal populations. This is a town off the coast of Maryland. This is actually the town that I grew up. I grew up in a condominium just off the picture here, like over here. This is Ocean City. And it's kind of, when you live in Ocean City, it doesn't look like this. It actually looks a little prettier than this. But when you fly, we paid my father to fly in a plane and get this shot because I knew I'd need this for many talks, and I've used it so many times. And so my dad took this picture flying in a plane over Ocean City. But when you get this aerial perspective of Ocean City, you kind of see that, man, it's kind of insane that there's that much infrastructure and there's that much concrete piled on top of what is a glorified sandbar. But I'm not judging those people necessarily, or my father. He's a real estate agent too, by the way, which is kind of interesting. Those places, these coastal locations, are rich economic markets. There's investment opportunities there. There's supply and demand. People are debating whether or not they want to buy a condominium, buy a house, whether they want to vacation there, maybe open it up for rent. There's quite a bit of investment opportunity. So, and not only that, clearly it matters where you're located. I mean, the fact that there's a beach here, that's part of the reason this density looks like this. If you just drive that way a little bit, it looks nothing like this. It's just farmland. So how do you put all this into in a computer with equations? Well, the way that you do it is you come up with equations that mimic the behavior of a number of different actors. And all of the actors, you give them goals. And as you can tell by the faces here, some of you recognize these faces, I can tell. The goals of these actors are to maximize profit and make a lot of money. Weirdly, it was not hard at all to find them with smiles on their faces. Warren Buffett, every picture of him, you see smiling. Yeah. And so the actors in the model, when you prescribe the economics that control their behavior, they want to maximize profit. And the way that they do that is they are basically making investment decisions in the model. So the way that they do that is, first of all, they're considering the possibility of purchasing a coastal property. They weigh that against the return that they might get on some other safe investment. Then they, of course, consider, well, if I'm going to invest in this coastal property, what amount of income might I get from this coastal property? So those are the things that they consider in the sense of possible gains from their investment. There also are going to be costs that they are going to have to pay. Insurances, taxes, those kinds of things. And then costs associated with how much they expect damage to occur in the future. Right? So if they have to say to themselves, well, if I'm going to buy this house, how much do I think over the lifetime of my mortgage am I going to have to pay for damages that are going to occur to this house? Effectively, insurance. They also have to consider, if they're going to live in a coastal environment, there may be some taxes associated with nourishing the beach. If they're going to engage, if their town's going to engage in beach nourishment and dune building, they're going to have to pay for that. So the actors then wrap all of those considerations in and generate from there a willing bid price for coastal property. So you have a whole suite of these actors, and they're heterogeneous. So they all come up with different bid prices. The reason that they're different is because they may have different expectations about what's going to happen in the future. So that allows them to have different bid prices, and then what you do is you effectively just auction off the properties. If you have, just to use numbers, if you have 100 properties for sale and there are 1,000 actors, you take the top 100 prices, and they're the ones that get the property, and that sets the price for the property. So you just match supply and demand, and that gives you an actual property value. And that's happening all the way as time is evolving in your model. These actors are making these decisions and bidding on coastal properties. Okay, so that model sits on top of the Barrier Island model that I described. You have properties being bought and sold on top of this physical environment, this simulated physical environment. But as we said when I started the talk, we also have to consider how the economy impacts the coastal dynamics in the form of beach nourishment. So beach nourishment, as I mentioned, just taking sediment from somewhere offshore and putting it out onto the beach to increase the width of the beach and or increasing the elevation of dunes to protect against storm surge. So the way that this is done in the model is relatively straightforward. You take these actors who bid on coastal properties. Once they become owners, then they engage in the following consideration. They want to protect their investment. So they perform a cost-benefit analysis, is the jargony term, just as we do when we decide whether or not we want to nourish Wrightsville Beach. So they perform a cost-benefit analysis. How much is it going to cost to nourish? What is the benefit to nourishing? Benefit being some damage reduction. If we don't nourish, we might suffer this damage. If we do nourish and build the dunes, we'll suffer less damage. So they look at the difference, and that's the benefit to mitigating. And so if they find that there's a positive cost-benefit analysis, they will enhance the beach, they'll nourish the beach, and they'll increase the height of the dunes in the physical model. Okay, so on the flip side, of course, the coastal environment impacts the coastal economy, as I mentioned, through storms, of course, and that happens in the model. If you have storm surges happening in the model, and there's coastal properties, and the storm surge overwhelms the beach, it can damage those coastal properties, and you just allow that to happen with the way that we know that it's happened in the past. But then in addition to that, you have people's expectations of what's going to happen in the future. And this is the most recently new part of this modeling endeavor. How to put people's expectations about what's going to happen in the future into a model like this. Because as these two images suggest, there's quite a spectrum in people's expectations. On one hand, you have 20 coastal counties informed by, I think, one soil scientist who has a master's degree, suggesting what's going to happen with sea level rise, and some people decide they want to listen to that. On the other hand, you have 99.9% of the most renowned scientists who have devoted their entire lives to studying sea level rise, suggesting what's going to happen with sea level rise. Some people listen to that. You may fall anywhere in this spectrum. But the important point is, there's quite a spectrum. Some people think the environment's going to do this. Some people think the environment's going to do this. So how do you put that into a model? Well, what I've done is the following. Those agents that I was describing, those actors in the model that I was describing, they come up with their expectations about what's going to happen in the future by combining two influences. One, they can look at past observations. They're sitting in the model. They can see what has happened through the course of history as the model's been running and take a look at what has been happening and project forward in the future. Or they can use science or some model to inform their future. So to elaborate, if you're trying to project or have some expectation about an environmental variable, say beach erosion, and you're right here in time, in the model, well, one thing that you could do is just look to the past and say, that's what's been happening in the past, so I'll just linearly project into the future, and that's what I think is going to happen in the future, and I'll base my investment decisions on that. That's one option. That's what I mean by observations. We would call those people observationalists in the model. Another possibility, of course, is you can, at that moment in time when you want to project into the future to see what's going to happen to, say, beach erosion, you can allow them to take the model that they're existing in and run the model forward in time and get some picture of how the future may evolve. And then they make their investment decisions, and then you let the model run into the future. It's a little bit science fiction-y, I realize it sounds kind of weird, but that gives them a much more sophisticated picture of what may happen into the future. And so I have this, just as an aside, I was looking today for a little cartoon image of a person sitting in a computer. It's probably hard to see this. I'm a little offended by what this person looks like. And being someone who sits at a computer every day, we're not all nerds just because we sit in front of a computer. So I spent some time looking around and I found this guy, which is a little cooler to me. He's got kind of a bear haircut. I like his shoes a little more. But the point being is that you can, so the actors in the economic part of the model, they have a mix of being influenced by these two factors in order to generate what's going to happen in the future. Okay? So we take all of these things, or I take all these things and wrap them into the model. The coastal dynamics part, you put the barrier island model in there, all the processes that I described. You put the coastal economic model in there, people are buying and selling properties up on top of the barrier island. You put decisions about beach nourishment, you put decisions about how I think I'm going to invest based on what I've been seeing or what some model is telling me is going to happen. And then you can now play games with, or you can adjust the future in a bunch of different ways. You can say, okay, let's run the model for a given sea level rise. Let's run it for some other sea level rise. Let's run it for some storm climate. Let's run it for another storm climate and see what actually happens. And so the results that I'm about to show you from what happens when you do that have come from initializing the model in a configuration that's similar to a coastal North Carolina town. It has those kinds of property values, and it has those kinds of physical beach characteristics. Okay? Okay, so the first result, just to get a feeling for how this model works, I ran it with a storm climate similar to what we've seen historically, and a rate of sea level rise of 3 millimeters per year, which is about what we've seen here in North Carolina over the past 50 years. Okay, and so what I'm plotting here is the results from one of those simulations. This plot is showing the property value through time, when time is measured in years down here. Okay? And so a couple things to point out in looking at that image. Number one, property value goes up, in the beginning, people buy and sell properties and they kind of settle on what they think the property value is at that moment in time. And then it sits there, and you do see these big dips in the property value. Some of them fairly large, like this one right here. That's a Hurricane Sandy type event. And that's exactly what's happening right now in New Jersey. The property values have been dramatically reduced. But as happens in the model and as happens in nature, those property values come back over the course of a year or two, a couple of years. However, what you notice right here is the plot didn't just come to an end. The simulation stopped because abandonment occurred. So what that means is that those actors in the model that are given rigorous and well thought out economic decision principles have decided at that moment in time that it is no longer worthwhile for them financially to buy coastal property. Nobody generates a bid price above $0. And it's not that they don't try to hold back what is happening at the coastline. This is the dune height through that same realm of time, and this is the beach width through that same realm of time. Looking at the beach width plot, these jagged marks, what's happening is you have erosion going on, nourishment occurs, that's when it ticks up, then erosion happens, nourishment kicks the beach back up. So they are definitely nourishing the whole time. And in fact, if you look closely, they're nourishing at a higher and higher frequency. So they're really trying their best to fight against beach erosion and the processes that are happening in the coastal environment. The same with the elevation of the dunes. The elevation of the dune is increasing through time. But even in spite of all those things, at some point they reach a moment in time where they abandon ship, they leave. It's quite a far distance into the future, I realize, in this particular simulation. But now it begs the question. We have knobs on this model. We can change things. We can change sea level rise. We can change the economic incentives to exist at that coastline. So let's see what happens when we do that. So this result, there's a lot going on here, so let me take this apart piece by piece. So this is what's called a parameter space plot. Not important. What is important is that this is, I've run a couple hundred simulations in this case, all at a low, what I call a low sea level rise, which is 3 millimeters per year, which is the rate of sea level rise we've seen for the past 50 years. And then what I vary in each of the simulations is two things. One, I vary how much it costs to go get the sand, how much you have to pay to nourish the beach per unit of sand. And then I vary the risk-free return that you get on coastal property. You can think of that like rent, effectively. And then what the colors correspond to is how long that simulation went before it abandoned. Okay, so to understand this, imagine picking a single cost of sand, $10 per cubic meter. And then if you move this way on the diagram, you're increasing the risk-free return on coastal property. And so the colors are going from blue to orange as you do that, which is saying that you are increasing your time to abandonment when you increase the risk-free return on coastal property. That makes sense. You are injecting the system with more economic incentive, and it's causing people to hold the fort even longer. If you pick a risk-free return on the property and move that way on the diagram, that is getting at increasing how much it costs to fight against nourishment, increasing the cost of sand. And so when you do that, you decrease the amount of time until abandonment. And so if many of you are probably looking in the upper left-hand corner right now, so that's the worst case scenario. Low return on the coastal property, very high cost to mitigate against beach erosion. In those cases, the time to abandonment can shrink down to around 100 years. So in 100 years-ish, economically, it does not make sense anymore to bid positively on coastal property. But it does kind of jive with what we think. The economic incentives play a large role in changing that time to abandonment. Over 250 years difference depending on where you are in that space. So if we take that same series of simulations but now run them for a high rate of sea level rise, which is a rate of sea level rise that's sort of a worst case IPCC projection, 10 millimeters per year. Now, similar behavior. Now you're still increasing time to abandonment as you increase the return on property, decreasing time to abandonment when you increase the nourishment and sand cost, but now the range is quite different. We're talking about the difference between 90 years and 35 years. So the number one, the economic incentives are playing less of a role in changing the amount of time to abandonment, but certainly overall, the time to abandonment is dramatically less than it was at the high rate of sea level rise.
When does your timeline start?
It's effectively, you could think of it as today,
So
plus or minus 5-ish
today,
years or something.
100 years
Yep.
ahead.
Yep, exactly. Okay, so one of the things that's interesting about a situation like this, the abandonment, is that from a scientific perspective, that represents a fundamental change in the behavior of the system. You're going from a system where you have a physical environment, people buying and selling coastal properties, and all of a sudden, everybody's out. So when they have changes like that in a market, a lot of times you would be or in a system in general, one of the very interesting things to ask is, are there any precursor signals to that dramatic change? In this case, a precursor signal to abandonment. And if you look at the model, it turns out that there are. Not in any of the environmental variables, but in some of the in one of the economic variables. This is a plot of the volatility of property value as a function of the years before people abandon. So in this plot, abandonment occurs right here at time 0. 100 means it's 100 years before the abandonment occurs. And I've done it for the two simulations I showed, the high rate of sea level rise and the low rate of sea level rise. And in both of them, right before abandonment, you get this dramatic increase in property value price volatility. This is not unlike what you see in the stock market. When you're talking about a single stock, if that stock eventually crashes, a lot of times you can look before the crash and see that the volatility of the trading went haywire before the stock crashed. The same thing happens in the model with property value. There's a lot of buying and selling. People start to realize trouble is right around the corner. And people are jumping in and out of the market and sort of getting panicky. And as they do, the volatility in property value spikes right before abandonment occurs. So it's a precursor signal to what happens. One of the other interesting things to do is to go back to this idea of how people generate their expectations of what's going to happen in the future and see what difference that makes. So in this result, what I have done is run two types of simulations. One simulation where every single actor in the economic market is what I call an observationalist. They only look at the past and project that into the future. Okay? And so I run a bunch of those simulations at different rates of sea level rise. And then I run simulations where you have a mix of observationalists and people who are informed by these sort of scientific models to figure out what's going to happen into the future. And that's the green plot at a bunch of different sea level rises. And the trend here, as you increase the rate of sea level rise, the trend in the damage that occurs, so this is the amount of property damage that occurs every year in those simulations, the trends are the opposite. When you have only observationalists, as you increase the rate of sea level rise, you are increasing the amount of property damage that occurs per year. When you have a market with observationalists and these model believers, the trend goes the other way. So this raises a very interesting equity issue, because who pays for these property damages? If the payment for these property damages is coming from outside the system, and outside the system, say, is comprised of people who are observationalists and model believers, but yet they're paying for property damage that is so heavily a function of whether you're an observationalist or model believer. If everyone at the coast is an observationalist, but yet this batch of people are having to pay for those damages, it kind of seems unfair. There's a significant dependence upon how people are projecting into the future when you calculate how much damage occurs. So the people who are paying for this property damage may or may not feel the same way about the future as the people who caused the property damage. It's an interesting equity issue. Okay, so just for the last, say, five minutes or so, what about now? So these are questions about the future. Some of this stuff's playing out over decades, many years. what can I say about the situation right now as it stands in communities like Wrightsville Beach, for example? Can I use this model to say anything useful in that regard? So I have to digress a little bit and talk about Pets.com. Pets.com is sort of the poster child company for the bursting of the dot-com bubble at the turn of the century. Pets.com went from popping onto the NASDAQ to complete liquidation in 286 days. When they first came onto the NASDAQ, they had about $600,000 in revenue they would generate in a year, and they were spending about $11 million on advertising. So, not surprisingly, Pets.com was a bubble, a financial bubble that burst. Economically, a sort of semi-formal economic definition of a bubble is that when the value of an asset is inflated relative to its fundamental worth. So in the case of Pets.com, when it first popped onto the NASDAQ, it was trading at $14 a share, yet they were losing millions of dollars every month as a company. So the value of the asset, that $14 a share, significantly inflated relative to their fundamental worth, which was negative millions of dollars. If I had given this talk 10 or 15 years ago, the idea of a bubble would be news to you. Many of us have been impacted by the bubble over the last few years, the housing bubble. Many of us have been impacted by it. The housing bubble, same process. The fundamental worth of houses became disconnected to what their actual trading asset value was. So one of the things that I'm going to talk about briefly is the possibility that these coastal properties might be in a bubble configuration, that the value, the intrinsic value of them might become divorced from what their actual property value is at any moment in time. So in order to do that, we have to go back to this picture and understand that if you want to ask questions about property value, if you buy all the things that I said at the beginning of the talk, you cannot do it just by considering economics. All of this stuff is a part of property value. It's not just the economics, it's how the coastline's evolving, it's how that's interacting with the economics, how the economics is then altering the coastline. And so beach nourishment, for example, is a fundamental component of property value. So then it begs the question, who pays for beach nourishment? Well, Wrightsville Beach, in the case of Wrightsville Beach, pays a portion of it, but the federal government comes in and pays a large portion of that mitigation. Okay? What if this were to disappear? That, because property value is all mixed up in this ball of dynamics, if you were to lose, if the cost to mitigate were to change, it would fundamentally alter property value. And if you don't believe me, this is actually work that I did not do, but this is my colleague Satya Gopalakrishnan at Ohio State. She has done this fantastic work to go out and determine how much beach width impacts property value. These are the kind of things economists do a lot, called regression analysis. But the idea of it is they do this. They go out there and they say, okay, she surveyed property values up and down the coastline of North Carolina. And then she's able to tease out each of the components of that property value. For example, if you have a 2-bedroom house versus a 3-bedroom house, how much is that worth? If you're next to good schools or not good schools, how much is that worth? And so she teases out each of those components. And one of the components that she was able to tease out was the width of the beach. So in other words, in feet, when you walk out from the dune line out to the ocean, how many feet is that? It turns out that how many feet that is makes a big impact on your property value. Specifically, she found out that for Wrightsville Beach, every foot that you increase the beach width, you add $10,000 to the property value. That's not trivial. Yeah. So what this is suggesting then, now if we go back to this picture I had up a moment ago, nourishment is a fundamental part of what the beach width is. And who pays for that is a part of this as well. And if it costs $1 trillion to nourish the beach, well, this beach width benefit's not going to be there. So the question hanging out there now is, historically, the cost of nourishment has been subsidized at a rate of about 66%. And we all agree, we just saw that beach width is an intimate part of property value, as is nourishment, because that's where we get beach width. So nourishment is an intimate piece of the property value. So what happens if you lose that subsidy? What if that subsidy were to disappear? Does that lead to a bubble? It does. So if I run simulations where I take the model that I just described to you and I have nourishment being subsidized by the federal government, and then I run the same simulation and nourishment is not subsidized by the federal government, there's a dramatic difference in the property value. This plot shows the fractional reduction in property value. So 0.30 means 30% reduction in property value as a function of the rate of sea level rise for two different storm climates, North Carolina and New Jersey. We probably want to focus on North Carolina because that's where we are. So look at the solid red line. So what that is saying is that, for example, if the rate of sea level rise turns out to be 7 millimeters per year, say over the next decade, and then if the government decided tomorrow, which they may be very likely to do, to remove the subsidy for beach nourishment, in that particular case, property value would be dropped by 25%. Now, it wouldn't happen immediately, I realize. It takes some time to unwind that position in the market. But the fundamental value, that's what this calculation is. The fundamental value of the property would decrease by 25% if the subsidy was gone in that case. In some of these other cases, for the high rates of sea level rise, you're talking about a nearly 40% decrease in the fundamental value of property. Okay, one last thing. So we can go back to that picture of abandonment and ask, what role does this subsidy play in dictating how long until abandonment occurs? So what I've done is run a whole bunch of simulations again, now for different rates of sea level rise and for different amounts of nourishment subsidy. So here 60 means the government is subsidizing 60% of nourishment. Here it means they're subsidizing 0% of nourishment. And what you find out is that, so for low rates of sea level rise, as you move this way and the government subsidizes more and more of that nourishment, that can actually have a dramatic impact on how long it takes till these simulations reach the abandonment point. However, when the rate of sea level rise is high, whether the government is subsidizing nourishment or not, abandonment comes relatively quickly, and government subsidy doesn't play a big role in dictating how long it is until nourishment occurs. So as a final thought, I promised that I would not show equations, but I'm showing a few. And I kind of want to bring this full circle. I mean, I realize that some of these ideas are relatively provocative. 40% decrease in property value and so forth. This is not politics. I don't have a lobby group telling me what I should or should not get out when I run these models. The things that I put into these models are very rigorous. They're equations that look like this. This is maybe 25% of the equations that exist in these models. Some of these equations have decades of history in the literature. I'm not dreaming this stuff up and just chunking it into the model. Some of this stuff comes with a long history of agreeing with data and people buy into what this equation is saying. What I have done, what's novel, is wrapping all of these things together, and in some cases creating some new equations as they are needed. And these are the results that you get. I'm not suggesting what you should or shouldn't do with these results. I'm not a politician. I'm a scientist, and it's science that is giving us these answers. Okay, so just to conclude, abandonment, the future of the coastline, given the decision between buying and selling coastal properties as it exists right now, and abandoning, eventually in these simulations, you reach abandonment. Now, if there's a loss of the government subsidy to nourish, that leads to a significant bubble in coastal property value. And then just with respect to the future of this work, I have been funded by NSF in the past. I've just submitted a big multi-institutional proposal to really lock this problem down and to investigate a few things that are kind of hanging out there. One is insurance. We have insurance in the model, but not in a very sophisticated way. And I think one of the things that we're proposing to NSF to do is to wrap insurance in a much more sophisticated way. The other thing that we need to do is provide these actors in the economic models with alternatives. If the decision is buying and selling coastal property as it exists right now or abandoning, well, those are two choices, but there's other choices out there as well. Alternative style housing, compensated retreat, something I don't know how many of you caught in the New York Times a few days ago, that in New York they're actually paying people in the wake of Hurricane Sandy for their properties. They're offering them 5 to 10% more than their property was worth before Sandy hit, and offering to buy their damaged home right now for that amount of value. So if that was an option in the model, that could lead to some interesting things. And these are the kind of things we propose to NSF to explore. But that, I will leave it at that. Entertain questions. So to answer, so you asked the question, who's paying for that?
Yeah.
That's part of that package, that $50 billion package to help those people recover. A big chunk of that is going towards this compensated retreat. But I haven't looked at this in detail, but one of the interesting things that you can do, a sort of back of the envelope calculation, I mean, they're pinpointing very specifically which homes they're actually willing to buy. If they tried to buy all of the homes that were damaged in coastal New Jersey alone, you're talking hundreds of billions of dollars. And that's just coastal New Jersey, that's not New York, and that's not all of coastal New Jersey. So the idea of doing this in mass for an entire coastline would take a significant financial resources. Yes? So you just go out? Yeah, so sorry. So that was a question of how do you measure the sand? You know, I had this statistic that showed for every extra foot of beach width, you get $10,000 on your Wrightsville Beach property. So they actually went out with like GPS and marched off. Yeah, so they marched from the dune line, from basically when you walk onto the beach in the Wrightsville, as soon as you come over the path, from like right at that point out to the water. And they do some corrections for tides and things like this, but it's effectively the distance of dry beach that you have. And they measure it with GPS. Excuse me?
Goes to the high water line.
Yeah, so that I can't remember if they use the mean water line or the high water line. I actually can't remember, but yeah.
So if the house is down, half a mile down the beach, how wide? And the house away from it is only maybe 10 feet. So how do they determine from that? That's what I'm trying to understand. I've seen it out there for boats, and at the States, and I don't know if that was a survey or not.
So one of the things that, to be totally honest about it, it's not as simple as just going out in one moment in time and measuring what that beach width is. You have to have ways that you kind of understand what the average beach width is at a particular location through time. But then they do that and they find out that that impacts property value. Now there's so many other things that impact property value, and that's part of why these economists do what they do. I mean, they're able to tease out all those differences. So it's not as simple as looking at one house and saying that's got that beach width, this house has that beach width, that house is twice as much as this house, so beach width means this much. It's not quite that simple because you got to factor in location, how many bedrooms, how recently built, and when you wrap all of those things in there, they're able to isolate individual characteristics, and they find that beach width leads to $10,000. Each foot leads to $10,000. Yes.
It seems like we decided we were going to let a lot of other people take our risk. Years ago, somebody had a beach cottage. They built a simple little beach cottage. It might have been worth no more than $3,000 or $4,000. If the waves took it away, it wasn't that much of a loss. Now we build multi-million-dollar condominiums right in that spot, but we don't want anybody. We don't want to lose that money. And if it gets damaged, we want the government to pay for it. I just think we've lost our sense of proportion.
It's a fair point, yeah. Yes, back there.
Every year we're told that this is the year for the major storm that we should get, and we've seen the Northeast get hammered in the last year. When I was looking at your model and how you use sea level rise as the cause, it made me think about what would be the impact on your model instead of sea level rise, which seems like a more long-term, quiet thing, to have major storms as that cause, and how that would impact your whole model.
It's a good point. I'm sorry to make that clear, but they're both in there. Storms and sea level rise are in there. And what you find is that they both play a role. Sea level rise is what leads to the long-term increase in the precariousness of their position. But it is storms that have dramatic impacts on the economic market. And a lot of times in those model simulations, when abandonment occurs, it's often after a storm. That's when they decide that, I could go back and pay for the damage cost to rebuild what just happened in the storm, but things have become so sketchy here that I'm out of here. So it is, in fact, as you're suggesting, the combination of the two many times. Yes?
I guess I have a question about what is the trend to eliminate this subsidizing of renourishment?
I mean, I only know that as much as you do by reading the paper and seeing what's being said. I just read an article this morning about Carolina Beach is starting to engage in the kinds of calculations that need to be engaged in to imagine a future where they don't have that subsidy. There's been, I think it was a 50-year plan where the government sort of promised a certain subsidy for 50 years, and that's now expired. And so whether or not they're going to re-up for that subsidy at that amount is unknown. Maybe Obama's going to talk about it in an hour, I don't know. I doubt it. But in any case, all I can do is speculate in that regard. And to not be a scientist and speculate, I would say that it seems unlikely in the current economic climate that that's something that's going to last for too much longer.
So does the subsidizing come locally, on a county level, on state or federal level?
So
I don't live near beach, so
right.
I'm not aware of how it's funded.
So it's come, that 66% number is the number that has come from the federal government historically. And they've appropriated them. That's just money that has just been earmarked for these towns, and they use it for nourishing their beaches. But there's been discussions, these discussions of losing that subsidy have existed for 10 or so, maybe 15 years. Hasn't happened yet, but it's starting to seem increasingly likely that that may happen.
One more question. Let me ask a question. Have you considered a joint appointment in the Cameron School of Business?
Well, they probably pay more than the physics department. So.
Well, Dylan, you want to talk a little bit about, just give us like 2 minutes on your extracurricular activity with the university in terms of coaching and that kind of thing?
Yeah, sure, be happy to. So there's actually a picture right there, those kids in the blue t-shirts on the beach. So since I've come to the university, one of the things I've done has been to coach the surf team. And this sort of a pro bono thing, I knew some of the kids who surfed at the university when I came here, and we decided to formalize having a surf team, and we've been extremely successful competitively. It's generated a lot of wonderful attention from the community and a lot of support from the community. The current team captain of our surf team is here. I won't point him out, I don't want to embarrass him. You can probably look around and pick him out, I have a feeling. He's one of the buff guys, yeah. But no, so it's something that's been just a pleasure of being a professor here, and it's been just a service component of what I do. But it's been just really cool to interact with the local surfing community. Yeah.
Well, so for part of that, you may not know this because you haven't been here before, but we have Dume Gorham Jr. do an artwork design for each individual speaker based on something of their interest area.
So the surfboard would be bigger than that.
Shooting the pipe might be. Very cool. Thank you. Appreciate it. Thank you guys. And thanks again. Okay, so we have refreshments outside, and please spend some time talking to Dylan about his work or about anything else I'm going to ask him about.
Thank you.